Here's a video for you theory of everything builders about general dimensional framework. Today is September 9th, 2025, created by me, Nemo Jackson, and Quantum Technological Innovations, QTI. This explainer is for everyone building theory of everything models. Visit Multiverse and Associated Science page and Anti-de Sitter Conformal Field Theory group on Facebook. If you have any questions, send us a message. Before particles, before fields, before forces, there is temperature structure. Think of reality as organized by a spectrum with two bookends, the coldest possible state and the hottest possible state. Between those bookends, the spectrum is divided into frames, discrete slots, so energy and information can be staged, stabilized, and then guided into ignition, peak, and decay. This is the fundamental scaffolding many attempts at a theory of everything skip over. If you start from particles, you inherit their assumptions. If you start from temperature slots, you build the stage upon which particles later appear. Begin with the bookends. The absolute cold limit is T_min equals 0K, where motion vanishes. At this bound, potential energy is maximized but locked, unable to express as kinetic motion. The absolute hot limit is T_max equals T_p 1.416808x10, circumflex 32K, the Planck temperature, where conventional descriptions break down. Here, potential energy rapidly converts to radiation and kinetic energy. These two anchors define the span that every model must respect, whether you're working on cosmology, condensed matter, or quantum gravity. Now the key idea, the temperature span is discretized into slots, frames distributed across a chosen spatial scale and a chosen time cadence, so manifestation can be quantified and compared. The indexing equation is S equals T dt x c x dt L. Here S is the slot index, T is the temperature at an event, dt is the chosen temperature step per slot, c is the speed of light, dt is the frame duration, L is the spatial scaling factor you choose, which can correspond to a light year or any relevant length scale. Read this as frames per second per spatial length. As you increase t, as you change the cadence dt, or as you observe over larger L, you change which slot is active and how energy expresses itself. To explain ignition, sustainment, and decay, use a manifestation function that encodes how potential energy is converted and balanced. Ms equals sin alpha, T_max, beta, T_min, plus gamma, dt, T_max. Ms is the manifestation in a given slot. The coefficient alpha describes ignition, the release of stored potential energy into motion or radiation. The coefficient beta describes decay, the way energy sheds back toward lower temperature structures. The coefficient gamma stabilizes the process, the tendency of a slot to hold equilibrium as conditions change. Notice how T/T_max captures proximity to the hottest bound, T/T_min reflects how far you are from the coldest bound, and dTT_max encodes how coarse or fine your temperature slotting is. Together, alpha, beta, and gamma teach you whether a slot prefers to build, to hold, or to release. A whole universe or a whole model is just the superposition of all active slots. U equals sin sigma ms, for S equals sin 1, n. U is the total state, the result of summing manifestations across n slots. Even if reality feels continuous, the sum reminds you it is discretely staged. This is important, it allows you to localize cause and effect. A change in cadence dt or scale L or a refinement of dt moves energy between slots without violating the bookends. That is exactly the discipline a theory of everything needs before introducing particle inventories, gauge groups, or curvature. How large is each slot's thermal window? Define it by the bookends and the count of slots. dt frame equals T_max, T_min, n. If you choose more slots n, you resolve finer thermal structure. If you choose fewer, you track broader phases. This is not an aesthetic choice, it determines what counts as a state in your model and what becomes an interaction between states. Many frameworks tangle these, but separating them with dt frame gives you a clean grammar for dynamics. You can merge the staging, decay, and scaling in one summary expression that you can compute at any cadence. U equals sin sigma, alpha, T_max, beta, T_min, plus gamma, dt, T_max, x, c x dt, L. This tells you, pick your thermal slotting dt, pick your observational cadence dt, pick your spatial scale L, and then measure how the balance of ignition, stabilization, and decay aggregates into a global state. If your result U is dominated by the alpha term across many slots, your system is in a build or ignition phase. If the beta term dominates, you are in a cooling and structure-releasing phase. If gamma holds steady, you are in a temporarily self-similar equilibrium. This is a diagnostic dashboard for any model, independent of what particles you later include. Let's unpack variables so anyone can implement this. T is temperature in Kelvin, the central driver of slot selection. T_min = 0K, the locked potential energy bound. T_max 1.416808 x 10 circumflex 32K, the Planck bound where new physics is expected. dt is the temperature step that defines a single slot. dt is the time step that defines your frame cadence. L is the spatial scaling length that defines your observational patch. C is the speed of light, setting causal pacing between frames and scales. S is the slot index you compute from T dt, dt and L ms is the manifestation measured in each slot. U is the sum over slots, the system-level output you will compare to observations. Alpha, beta, gamma are coefficients you calibrate to represent ignition, decay, and stabilization in your domain. Potential energy, PE, is the stored energy that can convert into kinetic, thermal, or radiant forms depending on slot conditions. How does potential energy manifest differently across slots? In cold slots near T_min, PE is largely locked. It mainly stores in positional configurations, elastic reservoirs, chemical binding, or vacuum-like baselines. As you climb slots, the alpha term releases PE into organized motion and radiation, and you will see rising kinetic signatures. Near the hottest slots, PE rapidly dumps into high-frequency radiant channels. Stability depends on gamma to hold any structure at all. When a system moves back down the slots, beta dominates and you watch ordered energy step down into lower temperature reservoirs, spreading and thinning. This three-phase cycle, ignite, hold, decay, is the universal handshake that your model must capture before you name a single particle. Why is this framework fundamental before particles? Because particles, fields, and couplings are outcomes that ride on top of energy staging. If you do not first specify how the temperature spectrum is discretized into slots across time and scale, your later definitions of state, interaction, and measurement will be ambiguous. The slot grammar removes that ambiguity. It tells you what counts as a state, a slot at a given T window, what counts as an interaction, motion between slots, and how to compute global behavior, the sum U. Only afterwards should you populate the slots with particle content, symmetries, or curvature. In other words, build the stage, then cast the actors. How do you choose dt, dt, L and the coefficients alpha, beta, gamma? Start from the phenomena you're modeling. If you are studying early hot phases, pick a smaller dt near T_max to resolve ignition behavior. If you are studying long cooling tails, widen dt far from T_max to compress the gentle slope. Set dt by the time scale of the signals you can measure. Milliseconds for lab plasmas, millions of years for cosmology. Pick L to match your observational patch, meters for experiments, parsecs for astrophysics, then calibrate alpha, beta, gamma against reproducible data, alpha scales with observed energy influx rates, beta with cooling rates, and gamma with measured dwell times in quasi-steady regimes. The point is simple. The slot framework is universal, the numbers are domain-specific. Common mistakes this fixes. First, mixing states and interactions. Slotting forces you to define a state by a temperature window and an interaction by motion between windows. Second, overfitting particle lists to explain thermodynamic behavior. Slotting explains much of the behavior before particles are even specified. Third, missing scale-time coupling. The factor, C, X, D, T, or L, makes you check whether your cadence and scale are consistent with causal propagation. Fourth, ignoring bookends. Repeatedly check results against T_min and T_max. If your model implies temperatures outside the span without justifying new physics, you know exactly where the inconsistency is. Implementation checklist for theorists and engineers. 1. Declare T_min, T_max, dt, dt, L. 2. Compute S from S equal sign, T, dt, X, Cx, dt, L. 3. Assign alpha, beta, gamma based on your system's ignition, decay, and stabilization evidence. 4. Compute ms for your active range of slots. 5. Sum U equals sine sigma ms to get the global state. 6. Compare U against measured observables and iterate dt, dt, L and coefficients until residuals are minimized. 7. Only then attach particles, fields, and geometries appropriate to the resolved slots. This discipline makes your theory legible, testable, and portable. Closing guidance. The hottest and coldest temperatures are the bookends of manifestation. The spectrum between them is not a blur, it is staged in frames, slots, that regulate how potential energy is converted into kinetic and thermal energy and then decays. The equations here give you a neutral universal grammar you can apply before any particle hypothesis. If you want help mapping this framework to your domain, we provide and help people. Visit my Facebook pages, DM me for questions, created by me, Nemo Jackson, and Quantum Technological Innovations, QTI.